Welcome, get comfortable, take a deep breath. Tonight, we're going to explore one of the universe's most profound mysteries, black holes. Objects so strange, so extreme, that they challenge everything we think we know about reality itself. Allow yourself to relax. Breathe deeply. Feel your eyes getting heavy and your body getting light. Let the tension release slowly through the tips of your fingers with each breath. Breathe out as the tension melts away. And as you drift off to sleep, follow me on this extraordinary journey to the limits of the known universe, and perhaps to the brink of the unknown and beyond. It sounds impossible, but there are places in our universe where the rules of physics as we know them simply stop working. Places where time doesn't flow the way it does here on Earth. Places where space itself is twisted into shapes we can barely comprehend. These places are called black holes. Nothing can escape a black hole. Not rocks, not gas, not planets, not even light itself. The fastest thing in the universe, traveling at 300,000 kilometers per second. Once something crosses the boundary of a black hole, it is gone from our universe forever. This isn't science fiction. This is real. Black holes test the absolute limits of physics. They sit at the boundary between Einstein's theory of gravity and the quantum world of the very small. At their centers, our equations break down completely. Mathematics gives us infinity as an answer, which usually means we've reached the edge of what we understand. And yet, despite how strange they are, black holes may hold the keys to our deepest questions. Questions about the nature of space and time. Questions about what happens to information in the universe. Questions about how gravity and quantum mechanics might finally be united into one complete theory. A black hole is a region of space where gravity is so overwhelmingly strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. It's not an empty hole, despite the name. It's an extremely compact concentration of matter, crushed down to extraordinary density. At the very center, according to our current theories, lies what's called a singularity, a point where matter is compressed to effectively infinite density, where the curvature of space-time becomes infinite, where our understanding breaks down. But we're getting ahead of ourselves. To truly understand black holes, we need to go back in time. Back before anyone had even heard the words black hole. Back to when they were just a wild idea in the mind of one curious scientist. The year was 1783. Albert Einstein wouldn't be born for another century. His theory of relativity was still more than 130 years away. And yet, a British natural philosopher named John Michell was already thinking about objects that sound remarkably like black holes. Michell started with what he knew: Newton's laws of gravity, the idea that light was made of tiny particles, like little bullets flying through space, and the concept of escape velocity, the speed you need to completely escape from a massive object. He asked himself a question: what if there was a star so massive, so dense, that even light particles couldn't escape from it? Using Newtonian physics, Michell calculated the escape velocity for different sized objects. He knew the approximate speed of light from earlier measurements, and he worked out that if a star had roughly the same density as our sun, but was about 500 times larger in diameter, its escape velocity would exceed the speed of light. Light particles shot upward from such a star could never get away. They would fall back down, pulled by gravity. The star would be dark, invisible a dark star, as he called it. This is strikingly close to the modern concept of a black hole. The key insight that an object with escape velocity greater than light speed would be invisible remains correct even today, though for different reasons than Mitchell understood. But here's where Mitchell showed real brilliance. He realized these dark stars wouldn't be completely undetectable. Even if they emitted no light, their gravity would still affect nearby objects. He suggested looking for bright stars orbiting around invisible companions as a way to find them. This is exactly how astronomers find black holes today, more than 2 centuries later. Around the same time, the French mathematician Pierre-Simon Laplace was thinking along similar lines. He too discussed massive bodies from which light could not escape. But like Mitchell's work, these ideas were eventually set aside and largely forgotten. Why? Because light, it turned out, doesn't actually slow down when climbing out of a gravitational field. Its speed in a vacuum is constant, as Einstein would later show. So the Newtonian picture of light as slowed down particles wasn't quite right, but the core idea that gravity could trap light would return in a new and more profound form. In 1915, Albert Einstein completed his general theory of relativity. It was a revolutionary new way of thinking about gravity, not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy, Einstein showed, bend and warp the fabric of space-time. Objects moving through this curved space-time follow the straightest possible paths, which appear curved to us. This is what we call gravity. The mathematics of general relativity are complex. Einstein himself wasn't sure the equations could be solved exactly for realistic situations. But within months, a German physicist named Karl Schwarzschild found an exact solution. Schwarzschild was serving on the Russian front during World War I when he did this work. Despite the harsh conditions, he solved Einstein's equations for the space-time around a perfectly spherical, non-rotating mass. What Schwarzschild found was remarkable. His solution showed that if you compressed enough mass into a small enough volume, space-time would curve so extremely that it would form a boundary, a surface of no return. This boundary would mark a region where the required escape velocity equals the speed of light. Outside this surface, light and matter could escape. Inside, every possible path leads inexorably inward. Nothing could get out. This critical radius, now called the Schwarzschild radius, depends only on the mass of the object. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it would be less than a centimeter. Schwarzschild had discovered the event horizon, though that term wouldn't be coined for decades. At first, most physicists, including Einstein himself, doubted these objects could form in nature. They seemed too strange, too extreme. The solutions were mathematically interesting, but surely nature wouldn't actually create such bizarre objects. The singularity at the center, where the equations predicted infinite density and curvature, seemed especially troubling. Many thought this infinity was a sign that the theory must break down, or that something would prevent such complete collapse. It would take decades and the work of many brilliant minds before black holes transitioned from mathematical curiosities to accepted parts of our universe. To understand how black holes actually form, we need to understand the life cycle of stars. Stars are born from clouds of gas, mostly hydrogen, that collapse under their own gravity. As the gas compresses, it heats up. Eventually, the center becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. This energy creates an outward pressure that balances the inward pull of gravity. For millions or billions of years, the star exists in equilibrium. Gravity squeezing inward, fusion pressure pushing outward. But fusion can't last forever. Eventually, the star runs out of hydrogen fuel in its core. What happens next depends on the star's mass. Our sun, a medium-sized star, will eventually swell into a red giant. It will shed its outer layers, creating a beautiful planetary nebula. The core left behind will be a white dwarf, an Earth-sized ember supported by quantum pressure from electrons. It will never become a black hole. The sun simply doesn't have enough mass. For a white dwarf to remain stable, there's a limit to how much mass it can have. This limit was calculated by Subrahmanyan Chandrasekhar in the 1930s. It's about 1.4 times the mass of the Sun. Above this Chandrasekhar limit, electron pressure isn't enough to support the star against gravity. For stars more massive than this, collapse continues. Electrons are forced to combine with protons, creating neutrons. What remains is a neutron star, incredibly dense, with all the mass of a star compressed into a sphere just 20 kilometers across. But there's a limit here too. Neutron stars can exist only up to about 2 to 3 solar masses. Above this, not even neutron degeneracy pressure can hold up against gravity. When a star is born with more than about 20 to 25 times the sun's mass, something dramatic happens at the end of its life. These massive stars burn through their fuel much faster. They create heavier and heavier elements through fusion, building up layers like an onion. Iron at the core, silicon around it, then oxygen, carbon, helium, and hydrogen in the outer layers. But fusion of iron consumes energy rather than releasing it. Once the core becomes iron, fusion stops. Support vanishes. What happens next occurs in less than a second. The core, now with nothing to hold it up, collapses catastrophically. It falls inward, compressing to nuclear densities. The outer layers, suddenly unsupported, fall inward as well, then bounce off the incompressible core and explode outward in a supernova. The explosion is spectacular. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. But we're interested in what's left behind. If the collapsing core has more than about 3 solar masses, nothing in the known universe can stop the collapse. Not electron pressure, not neutron pressure, nothing. The core continues to collapse, compressing smaller and smaller. It crosses its Schwarzschild radius and forms an event horizon. From the outside, the collapse appears to freeze at the horizon due to time dilation. But in the star's own reference frame, the collapse continues inexorably. A black hole is born. This is the most common way stellar mass black holes form, through the death throes of massive stars. Most stellar mass black holes have masses of a few to a few tens of times the sun's mass, though some can reach over 100 solar masses. But here's something profound. In principle, any mass could become a black hole if compressed into a small enough volume. It's not about what the object is made of, it's about density. If you could compress Earth down to about the size of a marble, it would become a black hole. If you could compress Jupiter to roughly the size of a soccer ball, it too would form a black hole. Of course, there's no known natural process that would compress planets this way, but it illustrates an important point. Black holes aren't a special state of matter. They're what happens when matter, any matter, is compressed beyond a critical density. Black holes come in different sizes, from the relatively small to the almost incomprehensibly massive. Stellar mass black holes, the kind formed from collapsing stars, typically range from a few to a few tens of solar masses. The smallest confirmed black hole is about 5 solar masses. The largest stellar mass black holes detected so far are around 100 solar masses, or slightly more. Then there are supermassive black holes. These giants lurk at the centers of large galaxies, including our own Milky Way. They can weigh millions to billions of times the mass of the Sun. The supermassive black hole at the center of our galaxy, Sagittarius A star, is about 4 million solar masses. That sounds enormous, but it's actually modest compared to the true giants. The black hole at the center of the galaxy M87 star, the first one ever imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. Some supermassive black holes are even larger, reaching tens of billions of solar masses. Between these two extremes, there's a somewhat mysterious intermediate category. Intermediate mass black holes might range from hundreds to hundreds of thousands of solar masses. These are harder to detect and study, and their existence and formation mechanisms are still being investigated. Intermediate mass black holes might form in dense star clusters, where repeated mergers of stars and stellar remnants gradually build up a more massive black hole. They might also represent a transitional stage in the growth of supermassive black holes. Nearly every large galaxy studied so far appears to host a supermassive black hole at its center. This isn't a coincidence. There seems to be a deep connection between the growth of galaxies and the growth of their central black holes, though the details are still being worked out. As for how common black holes are overall, the numbers are staggering. Astronomers estimate there could be tens of millions to hundreds of millions of stellar mass black holes in the Milky Way alone. That's just in our galaxy. When you scale up to all galaxies in the observable universe, the total population of stellar mass black holes is estimated to be around a quintillion, 10 to the power of 18, or possibly even more. Most of these black holes are quiet. They're not actively feeding on surrounding material, so they don't emit X-rays or other radiation. They're simply dark, compact masses floating through space, detectable only through their gravitational influence. This brings us to a fascinating question. How do we find something that's invisible? Black holes don't emit light. They're black, after all. So how do astronomers find them? The answer is, we look for their effects. We look for what they do to the space and matter around them. One of the most effective methods is looking for X-ray binaries. These are systems where a black hole orbits a normal star. As the black hole's gravity pulls gas from the companion star, that gas spirals inward, forming a rotating disk called an accretion disk. The gas in the accretion disk is compressed and heated by friction and gravitational forces. It becomes extraordinarily hot, millions of degrees. At these temperatures, it emits intense X-rays. We can't see the black hole itself, but we can see the brilliant X-ray glow of the superheated gas spiraling toward it. One of the first objects identified this way was Cygnus X1, discovered as a bright X-ray source in the 1960s. When astronomers looked at that region of sky with optical telescopes, they found a massive blue supergiant star. The star appeared to be orbiting something massive and invisible. By measuring how fast the visible star was moving and applying Newton's laws of motion, astronomers could calculate the mass of the unseen companion. It turned out to be far too massive to be a neutron star, the only other known type of ultra-compact object. In 1971, observations by Paul Murdin, Louise Webster, and others provided strong evidence that this invisible companion was a black hole. Cygnus X1 became the first object widely accepted as a black hole, and it helped convince the scientific community that black holes weren't just mathematical abstractions, but real objects in our universe. The Uhuru X-ray satellite, launched in 1970, was instrumental in this discovery. It provided some of the first space-based X-ray observations, building the case for black holes in binary systems. From space, above Earth's atmosphere, which blocks X-rays, astronomers could finally see this high-energy universe. Another powerful method for detecting black holes is watching how they affect the orbits of nearby stars. At the center of the Milky Way, astronomers have been tracking individual stars for decades. One star in particular, called S2, orbits something invisible at the galactic center. S2's orbit is highly elliptical, bringing it very close to the center every 16 years. By precisely measuring S2's position and velocity over many years, astronomers Andrea Ghez and Reinhard Genzel and their teams showed that it's orbiting an object with about 4 million times the Sun's mass, compressed into a region smaller than our solar system. There's nothing visible there, no cluster of stars, no giant gas cloud, just an enormous mass in a tiny space. The only explanation is a supermassive black hole, which we now call Sagittarius A star. For this work, Ghez and Genzel shared the 2020 Nobel Prize in Physics. Accretion disks themselves provide clues beyond just emitting X-rays. The X-rays often flicker on millisecond timescales. This rapid flickering tells us the emitting region must be very small, only a few hundred kilometers across. Only an extremely compact object like a black hole could produce such rapid variations. From these various lines of evidence, astronomers have now identified a few dozen stellar mass black holes with very strong certainty. Many more objects are classified as black hole candidates, and with each passing year, as our instruments improve, the list grows longer. Near a black hole, the familiar rules of space and time start to behave in strange and counterintuitive ways. Let's start with light. Light always travels in straight lines, right? Well, not exactly. Light travels along the straightest possible paths, what mathematicians call geodesics. But when space-time itself is curved by mass, those straightest paths are no longer straight in the ordinary sense. Think of it this way. If you draw a straight line between two cities on a globe, the shortest path is actually a curve, a great circle route, because you're working on a curved surface. Similarly, near a black hole, light follows the curves of space-time. This bending of light creates gravitational lensing. Light from a background star or galaxy passing near a black hole can be bent around it, creating multiple images, arcs, or rings. In extreme cases, light can loop partway or almost completely around the black hole before escaping. The result is that we can see objects that are directly behind the black hole, bent around it by gravity. As light climbs out of a deep gravitational well, another effect occurs. The light loses energy. This energy loss causes its wavelength to stretch, shifting it toward the red end of the spectrum. This is called gravitational redshift. Close to the event horizon, this redshift becomes extreme. Light that manages to escape becomes heavily dimmed and shifted to longer wavelengths. An object falling into the black hole would appear redder and fainter to a distant observer as it approaches the horizon, eventually fading from view entirely. Now let's talk about time. Time flows differently in different gravitational fields. This isn't just a theoretical prediction, it's been measured. GPS satellites have to correct for the fact that time runs slightly faster in their orbits than it does on Earth's surface. Near a black hole, these time dilation effects become extreme. Imagine you're watching a friend fall toward a black hole from a safe distance. As your friend approaches the event horizon, you would see them moving slower and slower. Their clock would appear to tick more and more slowly. Light from them would become increasingly redshifted. From your perspective, your friend would never quite reach the event horizon. They would appear to freeze there, asymptotically approaching, but never crossing, fading from view as their light becomes too redshifted to detect. But from your friend's perspective, something very different happens. Their own clock ticks normally. They feel nothing special as they cross the horizon. They pass through in a finite amount of their own time, perhaps just seconds or minutes for a stellar mass black hole. This is one of the most mind-bending aspects of relativity. Two observers can genuinely experience time passing at different rates. There's no paradox. Both perspectives are valid within their own reference frames. For rotating black holes, things get even stranger. A spinning black hole drags space-time around with it. This effect is called frame dragging. It's as if the black hole is stirring space-time like honey. In a region called the ergosphere, which extends beyond the event horizon, space-time is dragged so strongly that nothing can remain stationary relative to distant observers. Everything must rotate in the same direction as the black hole, whether it wants to or not. This might sound like a problem, but it's actually an opportunity. In principle, energy can be extracted from a rotating black hole through processes like the Penrose process. You could, in theory, drop something into the ergosphere in just the right way and extract energy from the black hole's rotation, slowing it down while gaining energy. Whether any natural process or future civilization might actually do this remains an open question, but the physics allows it. The event horizon is perhaps the defining feature of a black hole. It's the boundary that makes a black hole a black hole. But what exactly is it? The event horizon is a surface in space-time beyond which events cannot affect an outside observer. It's the point of no return. Cross it, and you can never come back. Send a signal from inside, and it will never reach the outside universe. It's not a physical surface. There's nothing solid there. An astronaut crossing the event horizon of a supermassive black hole wouldn't feel anything special at that exact moment. No wall, no barrier, no sudden change. And yet, it's a profound boundary. Outside the horizon, there exist possible trajectories for light and matter that lead back out to distant space. Inside the horizon, every possible future path curves inexorably inward toward the singularity at the center. The size of the event horizon depends on the black hole's mass. For a non-rotating black hole, the radius is simply proportional to the mass. This is the Schwarzschild radius. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a supermassive black hole with 1 billion solar masses, it's about 3 billion kilometers, roughly 20 times the distance from Earth to the Sun. The event horizon of a rotating black hole is slightly smaller and more complex in shape, but the basic principle is the same. It marks the surface beyond which escape becomes impossible. One common misconception is that a black hole is like a cosmic vacuum cleaner, sucking everything in from vast distances. This isn't true. Far from the black hole, its gravity is no different from any other object of the same mass. If the Sun were suddenly replaced by a black hole of the same mass, Earth's orbit wouldn't change at all. We'd freeze in the dark, but we wouldn't be pulled into the black hole. The gravitational effect at Earth's distance would be identical. It's only very close to a black hole, within a few times the Schwarzschild radius, that things become unusual. That's where orbits become unstable, where light paths are dramatically bent, where time dilation becomes severe. The event horizon also has a deep connection to information and entropy. In the 1970s, physicists realized that black holes have a temperature and entropy, just like ordinary thermodynamic systems. The entropy is proportional to the area of the event horizon, not its volume. This strange property, that information about a black hole is encoded on its surface rather than throughout its volume, hints at deep connections between gravity, quantum mechanics, and information theory. It's called the holographic principle, and it's still a major area of research. The event horizon is also what creates the black hole's shadow, the dark region visible in the famous Event Horizon Telescope images. This shadow is slightly larger than the event horizon itself, because light that passes just outside the horizon can still be captured or bent in such complex ways that it doesn't escape to form a clear image. For M87 star, the shadow has an angular size of about 42 microarcseconds as seen from Earth. That's equivalent to seeing a grapefruit on the moon. The fact that we can resolve this at all is a testament to the incredible precision of very long baseline interferometry. So what would it actually feel like to fall into a black hole? This is one of the most common questions people ask, and the answer depends greatly on the black hole's size. Let's start with the approach. If you were in free fall toward a black hole, you'd initially feel weightless. This might seem strange. Isn't gravity pulling you in? Yes, but gravity pulls everything equally. You, your spaceship, the air around you all accelerate together. Locally, you feel no net force, just like astronauts on the International Space Station. This is actually one of Einstein's key insights. Free fall in a gravitational field feels exactly like floating in deep space with no gravity at all. It's called the equivalence principle. But as you get closer to a small black hole, you'd start to feel something else: tidal forces. Tidal forces arise because gravity gets stronger the closer you are to the source. Your feet, being closer to the black hole than your head, would feel a stronger pull. This difference in gravitational force would stretch you lengthwise. At the same time, the gravitational field would squeeze you from the sides. You'd be stretched head to toe and compressed side to side. The result is called spaghettification, a term popularized by Stephen Hawking. For a stellar mass black hole, perhaps 10 times the sun's mass, tidal forces become lethal long before you reach the event horizon. You'd be torn apart, stretched into a thin stream of atoms, tens or hundreds of kilometers outside the horizon. This is a violent and immediate death. There's no possibility of crossing the horizon intact. But for a supermassive black hole, things are very different. The tidal forces at the event horizon depend on the black hole's mass. Surprisingly, bigger black holes have gentler tidal forces at their horizons. This is because the horizon is larger, so the curvature of space-time is less steep. For a supermassive black hole like Sagittarius, a star, with 4 million solar masses, tidal forces at the horizon would only be a few times Earth's gravity, uncomfortable, but not immediately lethal. You could, in theory, cross the event horizon of a supermassive black hole alive and intact. You might even survive for several minutes or longer inside, depending on the black hole's exact size and rotation. Of course, you'd still eventually be destroyed as you fell deeper and tidal forces grew stronger. But the crossing itself wouldn't be the instant of death. It would be quiet, uneventful from your perspective. Now, what would you see? As you fall, the outside universe would appear to speed up due to time dilation. Light from distant stars would be blue shifted, gaining energy, becoming brighter and bluer. You might see stars race through their life cycles in moments. In principle, you could see the entire future history of the universe compressed into the final seconds or minutes before you reach the singularity. Of course, the intense radiation from this blue shifted light would likely kill you, but it's a fascinating thought. The sky around you would distort dramatically. The sphere of the outside universe would appear to compress into a shrinking, bright circle. Behind you, the universe would squeeze down into a small, intensely bright disk. Once you cross the event horizon, you're in a realm where the usual rules of space-time are inverted. Inside the horizon, the direction toward the singularity becomes a direction in time, not space. Just as you can't avoid moving forward in time in the normal universe, inside a black hole, you can't avoid moving toward the singularity. All roads lead to the center. There is no possible path that leads back out or even stays at a constant distance. The singularity isn't just a place you're falling toward. It's in your future, as inevitable as tomorrow. The view of the external universe would fade. Light from outside can still reach you for a while, but as you fall deeper, even that becomes increasingly redshifted and dimmed from your accelerating reference frame. Eventually, perhaps after seconds or minutes, you'd reach the singularity, and there, our understanding ends. What is the singularity? This is where we must admit the limits of our knowledge. According to general relativity, the singularity is a point, or in rotating black holes, a ring, where space-time curvature becomes infinite, where density becomes infinite, where the laws of physics as we know them cease to make sense. Our equations literally give infinity as an answer, and in physics, infinity usually means we're missing something. It's a sign that our theory has reached its limits. General relativity is an incredibly successful theory. It's passed every test we've thrown at it. But it's a classical theory. It doesn't include quantum mechanics, and we know quantum mechanics is essential for understanding nature at very small scales and very high energies. Most physicists believe that a complete theory of quantum gravity will somehow resolve the singularity. Perhaps space-time itself has a quantum structure at the smallest scales, preventing true infinities from forming. Perhaps there's a smallest possible length, the Planck length, about 10 to the power of minus 35 meters, below which our usual notions of space-time break down. We don't know. We don't have a complete theory of quantum gravity yet. String theory, loop quantum gravity, and other approaches have made progress, but we're not there yet. Inside rotating black holes, the structure becomes even more complex. Mathematically, the solutions allow for inner horizons, regions called Cauchy horizons, where predictability in space-time can break down. Whether these features exist in real black holes or are artifacts of idealized solutions is still debated. There's also the possibility of wormholes or connections to other regions of space-time, at least in certain exotic solutions. But most physicists believe these features are either impossible in realistic black holes or would be violently unstable. The interior of a black hole remains one of the deepest mysteries in physics. It's a regime where gravity is strong. Quantum effects should be important, and we have no experiments or observations to guide us. We're left with mathematics, intuition, and educated guesses. But we're not completely in the dark. Even if we can't peer inside a black hole, we can study their exteriors, their event horizons, and their interactions with their surroundings. And these studies continue to teach us profound lessons about the nature of space, time, and matter. Black holes are not just cosmic destroyers. They're also architects of the universe. Black holes can grow by accreting matter, steadily pulling in gas from their surroundings. This gas doesn't fall straight in. Conservation of angular momentum causes it to spiral inward, forming a rotating accretion disk. The accretion disk can be incredibly bright. The gravitational energy released as matter falls toward a black hole can be converted to radiation with remarkable efficiency, sometimes 10% or more of the infalling mass energy. That's more efficient than nuclear fusion. This makes accreting black holes some of the brightest objects in the universe. Active galactic nuclei, powered by supermassive black holes feeding on gas in the centers of galaxies, can outshine all the stars in their host galaxies combined. Some black holes also launch powerful jets. These jets are streams of plasma, accelerated to nearly the speed of light, that shoot out from the regions near the black hole's poles. These relativistic jets can extend for hundreds of thousands or even millions of light years, far beyond their host galaxies. How do black holes produce these jets? The exact mechanism is still being studied, but it involves the black hole's rotation, powerful magnetic fields threading through the accretion disk, and complex interactions between plasma and magnetic forces. The energy for the jets likely comes from the rotational energy of the black hole itself, or from the gravitational potential energy of the infalling matter. Through processes that tap into the black hole's spin, enormous amounts of energy can be channeled into these narrow beams. These jets have a profound impact on their surroundings. They plow into the intergalactic medium, heating gas, preventing it from cooling and forming stars. They can regulate the growth of galaxies, creating a feedback mechanism that links the evolution of the central black hole with the evolution of the entire galaxy. There's strong evidence that the mass of a galaxy's central supermassive black hole is correlated with properties of the galaxy itself, like the velocity dispersion of stars in the galactic bulge. This suggests a deep co-evolution. As the galaxy grows, so does the black hole, and the black hole's activity in turn affects how the galaxy develops. Black holes also grow through mergers. When two galaxies collide, their central black holes can eventually spiral together and merge, forming a single, more massive black hole. This merger releases tremendous amounts of energy in the form of gravitational waves, ripples in space-time itself that travel at the speed of light. There's even speculation that the growth of black holes over cosmic time could be connected to dark energy, the mysterious component that drives the accelerated expansion of the universe. Some recent studies suggest supermassive black holes might contribute to, or even help explain, dark energy, though this is still a controversial and developing idea. If this connection holds, it would mean black holes aren't just residents of the universe. They might actually be participants in determining the universe's ultimate fate. For most of history, black holes were theoretical, objects predicted by equations but never directly observed. That changed dramatically in the 21st century with two breakthrough technologies: gravitational wave detectors and the Event Horizon Telescope. Let's start with gravitational waves. When massive objects accelerate, particularly in asymmetric ways, they create ripples in the fabric of space-time. These ripples propagate outward at the speed of light, carrying energy away from the source. Einstein predicted their existence in 1916, but they're incredibly weak and difficult to detect. For decades, physicists tried to build detectors sensitive enough to measure gravitational waves. The challenge is immense. A gravitational wave passing through Earth stretches and squeezes space by an almost inconceivably small amount, less than 1,000th of the diameter of a proton, across a distance of kilometers. The breakthrough came with LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses laser interferometry to measure tiny changes the length of 4-kilometer-long arms. It's one of the most precise measuring instruments ever built. On September 14th, 2015, both LIGO detectors, one in Louisiana and one in Washington State, detected a signal. The signal lasted less than a second. It swept upward in frequency from 35 to 250 Hertz, then faded. This pattern, called a chirp, matches exactly what's predicted when two black holes spiral together and merge. The black holes were roughly 29 and 36 solar masses. They merged to form a black hole of about 62 solar masses. 3 solar masses of energy, nearly 10 to the 47th joules, was radiated away as gravitational waves in a fraction of a second. For comparison, that's more power than all the light emitted by all the stars in the observable universe combined, concentrated into a brief moment. This detection opened a new window on the universe. Gravitational wave astronomy allows us to observe events that emit little or no light, to study black holes directly through the space-time ripples they create. Since 2015, LIGO and its partner detector Virgo have detected dozens of black hole mergers. These observations have taught us about the population of black holes, their masses, spins, and how often they merge. Gravitational waves also let us test general relativity in the strong field regime. After two black holes merge, the resulting black hole settles down by emitting gravitational waves in a process called ring down. The frequency and damping time of these ring-down modes depend only on the final black hole's mass and spin, exactly as general relativity predicts. So far, every gravitational wave observation has matched Einstein's theory precisely. The theory has passed every test with remarkable accuracy. One particularly elegant test involved checking Stephen Hawking's prediction that the total surface area of black hole event horizons cannot decrease. When black holes merge, the area of the final black hole's horizon should be at least as large as the sum of the two original horizons. Gravitational wave observations have confirmed this prediction, providing another piece of evidence that black holes behave exactly as the theory says they should. Now let's turn to the other great observational breakthrough, the Event Horizon Telescope. The Event Horizon Telescope isn't a single telescope. It's a network of radio observatories spread across the entire planet, working together as one giant virtual telescope the size of Earth. The goal was audacious: to take a picture of a black hole's shadow, to resolve the region around the event horizon itself. This requires extraordinary angular resolution. The target, M87 star, is a giant black hole, but it's also 55 million light-years away. From Earth, its event horizon appears to have an angular size of only about 40 microarc seconds. That's like trying to see a donut on the moon. No single telescope can achieve this resolution, but by combining signals from telescopes separated by thousands of kilometers, using a technique called very long baseline interferometry, astronomers can synthesize the resolving power of an Earth-sized dish. Each participating telescope observes the same target at the same time. Recording the radio waves it detects along with ultra-precise timestamps from atomic clocks. Even timing errors of trillionths of a second would blur the image, so the timing must be perfect. Later, specialized supercomputers called correlators combine all the data, lining up the signals and measuring tiny differences in when the radio waves arrived at each telescope. These timing differences encode fine spatial detail about the source. The EHT operates at millimeter wavelengths, observing the radio emission from superhot gas in the accretion flow just outside the event horizon. The black hole itself is invisible, but the gas around it shines brilliantly at these wavelengths. The challenge is that the data is sparse. The telescopes sample only certain points on Earth's surface, not a continuous dish. Filling in the gaps requires sophisticated imaging algorithms and careful validation to ensure the final image isn't an artifact of the reconstruction process. Multiple independent imaging teams use different algorithms and techniques. They all converged on the same result: a bright ring of emission with a dark center, the shadow. On April 10th, 2019, the first image was released: M87 star, a supermassive black hole in the center of the giant elliptical galaxy M87. The image showed exactly what general relativity predicted: a bright ring of radio emission, roughly circular, with a dark central region about 2.5 times the size of the Schwarzschild radius. The dark region is the shadow, where light paths are either captured by the black hole or bent in such complex ways that they don't escape to form a clear image at our location. In 2022, the EHT released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This was even more challenging because Sagittarius A star is much smaller, and the gas around it changes on timescales of minutes, making it harder to reconstruct a sharp image. But again, the results showed a ring and shadow, confirming that our galaxy's central black hole looks just as general relativity predicts. These images are more than just pretty pictures. They're direct visual evidence that black holes exist, that event horizons are real, and that space-time behaves exactly as Einstein described more than a century ago. They represent the culmination of decades of work by hundreds of scientists around the world, and they mark the beginning of a new era in black hole astronomy, where we can not only detect these objects indirectly, but actually resolve their event horizon scale structure. Let's talk about the population of black holes and their distribution through space. Scientists haven't counted every black hole individually. That would be impossible. Most black holes are quiet, not actively feeding, and therefore don't emit radiation that we can detect. They're simply dark, compact masses drifting through space. But we can estimate their numbers based on what we know about star formation, stellar evolution, and the fraction of massive stars that end their lives as black holes. For stellar mass black holes, the ones formed from collapsing stars, astronomers estimate there could be roughly 100 million or more in the Milky Way alone. That's about one black hole for every few thousand stars in our galaxy. Most of these are too far away and too faint to detect individually with current technology. We've confirmed only a few dozen stellar mass black holes with very strong certainty, mostly in X-ray binary systems, where they're actively pulling gas from a companion star. Counting black hole candidates identified through gravitational waves, X-ray observations, and other methods, the number rises to hundreds or thousands, depending on how strict the criteria are for classification. When we scale up to the entire observable universe, with its hundreds of billions of galaxies, the total number of stellar mass black holes is staggering. Cosmological estimates suggest around 10 to the 18th power or more. That's a billion black holes, possibly many more. For supermassive black holes, nearly every large galaxy appears to host one at its center. With hundreds of billions of galaxies in the observable universe, that means hundreds of billions of supermassive black holes. Now, how close is the nearest black hole? The closest known black hole to Earth is called Gaia B-H1. It's a quiet stellar mass black hole in a binary system with a sun-like star, at a distance of about 1,560 light-years. That might sound close on cosmic scales, and it is. 1,560 light-years is in our galactic neighborhood, practically next door in astronomical terms. But it's still incredibly far by human standards. Light itself, traveling at 300,000 kilometers per second, takes 1,560 years to make the journey. If you could somehow travel at the speed of light, which is impossible for anything with mass, it would still take over 1,500 years to reach Gaia B-H1. At more realistic speeds, the journey times become almost incomprehensible. Earth orbits the Sun at about 30 kilometers per second. If we could maintain that speed in a straight line toward Gaia B-H1, the journey would take roughly 15 to 16 million years. Our fastest spacecraft, the Parker Solar Probe at its maximum speed, reaches about 190 kilometers per second. Even at that incredible velocity, the trip would still take more than 2 million years. So while Gaia B-H1 is our closest black hole neighbor. It remains impossibly distant by any practical measure. We will not be visiting it anytime soon. There may be closer black holes that we haven't discovered yet. Perhaps wandering black holes that aren't in binary systems and therefore don't emit X-rays. Perhaps primordial black holes, if they exist, could be much closer. But based on what we've detected so far, Gaia BH1 holds the record. It's worth noting that despite having stellar mass black holes scattered throughout the galaxy, we're in no danger from any of them. Space is vast. The distances are enormous. The probability of a black hole passing close to our solar system is vanishingly small. Black holes are remarkable objects, but they're not cosmic vacuum cleaners. They don't roam around sucking up everything in their path. From a distance, they're gravitationally no different from any other object of the same mass. They're simply very, very compact. Before we explore the remaining mysteries, let's take a moment to recognize some of the brilliant minds who transformed black holes from wild speculation to established science. We've already mentioned John Michell, the English clergyman and natural philosopher, who in 1783 proposed the idea of dark stars from which light could not escape. His insight, using Newtonian physics and the corpuscular theory of light, was remarkably prescient. Karl Schwarzschild, a German physicist and astronomer, found the first exact solution to Einstein's field equations in 1916, just months after General Relativity was published. He did this work while serving on the Russian front during World War I. Tragically, he died later that year from an illness contracted at the front. He never lived to see how important his solution would become. Subrahmanyan Chandrasekhar, known as Chandra, calculated the maximum mass of white dwarfs in the 1930s. This Chandrasekhar limit showed that above about 1.4 solar masses, white dwarfs cannot exist, forcing continued collapse. This work was initially controversial, but eventually earned him the 1983 Nobel Prize in Physics. The Chandra X-ray Observatory is named in his honor. J. Robert Oppenheimer, best known for leading the Manhattan Project, also made crucial contributions to black hole physics. In 1939, he and his student Hartland Snyder modeled the complete gravitational collapse of a massive star in general relativity. They showed that such a collapse could proceed indefinitely, forming what we now call a black hole. This was one of the first papers to really take the idea seriously. John Wheeler, an American physicist, did more than anyone to popularize black holes. In the 1950s and 60s, he clarified the physics of gravitational collapse and convinced the broader community that black holes weren't just mathematical curiosities, but real astrophysical objects. Most importantly, he coined the term black hole itself in 1967, giving these objects a memorable and evocative name. Before that, they were called frozen stars or collapsed stars. Roger Penrose, a British mathematician and physicist, proved powerful theorems about singularities in the 1960s. His work showed that once a trapped surface forms in general relativity, the formation of a singularity is inevitable under very general conditions. This made black holes robust predictions of the theory, not just artifacts of special, symmetric solutions. He received half of the 2020 Nobel Prize in Physics for this work. Stephen Hawking needs little introduction. His most famous contribution to black hole physics was showing in the 1970s that quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation means black holes have a temperature and entropy and can slowly evaporate over time. This discovery linked gravity, quantum mechanics, and thermodynamics in profound ways and continues to drive research today. Andrea Ghez and Reinhard Genzel led separate teams that, over decades, tracked individual stars orbiting the center of the Milky Way. Their measurements showed a compact, invisible object of about 4 million solar masses at the galactic center, confirming the presence of Sagittarius A star. They shared half of the 2020 Nobel Prize in Physics for this achievement. Multiple X-ray astronomers in the 1960s and 1970s, including Paul Murden, Louise Webster, and others, established the first strong stellar mass black hole candidates by studying X-ray binaries like Cygnus X1. Their observational work was crucial in convincing the community that black holes really exist. Rainer Weiss, Kip Thorne, and Barry Barish led the effort to build LIGO, the Laser Interferometer Gravitational Wave Observatory. The 2015 detection of gravitational waves from merging black holes was the culmination of decades of work by thousands of scientists and engineers. Weiss, Thorne, and Barish shared the 2017 Nobel Prize in Physics for this achievement. And finally, the Event Horizon Telescope collaboration, involving hundreds of scientists at institutions around the world, produced the first images of black hole shadows. This work required not only technical brilliance, but also international cooperation on an unprecedented scale. These are just some of the key figures. Many others have made essential contributions to our understanding of black holes. It's a testament to the power of human curiosity and collaboration that we've gone from theoretical speculation to direct observation in just over a century. One of the most puzzling aspects of supermassive black holes is how they got so big so fast. Observations of the early universe, looking back to when the universe was less than 1 billion years old, reveal galaxies with supermassive black holes already weighing billions of solar masses. This is strange. The universe was so young at that time. How did these giants form and grow so quickly? To understand the problem, we need to consider how black holes grow. The main mechanism is accretion, pulling in surrounding gas and matter. But there's a limit to how fast a black hole can grow through accretion. As matter falls toward a black hole, it heats up and emits radiation. This radiation creates an outward pressure that can push away additional infalling material. The maximum rate at which a black hole can accrete matter, called the Eddington limit, depends on its mass. Starting from a stellar mass black hole of, say, 30 solar masses, and growing at the Eddington limit continuously, you could reach 1 million solar masses in a few 100 million years. But to reach billions of solar masses in the time available requires either starting with much more massive seeds or finding ways to exceed the Eddington limit. Astronomers are investigating several possibilities. Perhaps some supermassive black holes formed from seed black holes created by the collapse of the very first, extremely massive stars in the early universe. These population 3 stars, as they're called, might have been hundreds of solar masses, leaving behind correspondingly massive black holes when they died. Alternatively, in dense early environments, massive gas clouds might have collapsed directly into black holes of thousands or even hundreds of thousands of solar masses, skipping the stellar phase entirely. These direct collapse black holes would have a significant head start. There's also the possibility that early black holes grew faster than the Eddington limit under special conditions, perhaps through particularly dense or cold gas accretion that reduced radiation pressure. And black holes can merge. In the crowded, chaotic early universe, black hole mergers might have been more common, providing another avenue for rapid growth. The truth is probably some combination of these mechanisms. Different supermassive black holes may have different formation histories, but the details are still being worked out, and every new observation of distant quasars and early galaxies provides additional clues. Understanding how supermassive black holes formed and grew in the early universe isn't just about black holes. It's about understanding galaxy formation and evolution, because the growth of galaxies and their central black holes appear to be intimately connected. Let's return to the powerful jets that some black holes produce and explore them in more detail. These relativistic jets are among the most energetic phenomena in the universe. They're streams of plasma accelerated to more than 99% of the speed of light, shooting out from the regions near a black hole's poles. How does this happen? The exact mechanism is still being studied, but the basic picture involves the black hole's rotation, magnetic fields, and the accretion disk. As gas spirals into a black hole, it carries magnetic field lines with it. These field lines can become twisted and wound up by the rotation of the disk and the black hole itself. The magnetic field can tap into the enormous rotational energy of the spinning black hole, or the gravitational energy of infalling matter, through complex magneto-hydrodynamic processes. These magnetic fields can channel plasma into narrow beams and accelerate it to relativistic speeds. The black hole's rotation may play a direct role through a process called the Blandford-Znajek mechanism, which extracts energy from the black hole's spin. The result is a pair of jets shooting out along the black hole's rotation axis in opposite directions. These jets can extend for millions of light years, far beyond their host galaxies. They plow into the intergalactic medium at nearly the speed of light, creating enormous structures called radio lobes that glow with synchrotron radiation. The impact of these jets on their environment is profound. They heat the surrounding gas, preventing it from cooling and condensing to form new stars. This provides a feedback mechanism that regulates both star formation and the growth of the black hole itself. Without this feedback, galaxies might form stars too rapidly, exhausting their gas supply too quickly. The supermassive black hole, through its jets and radiation, acts as a thermostat, keeping the galaxy in balance. This is one reason why the mass of a galaxy's central black hole is correlated with properties of the galaxy as a whole. They co-evolve, influencing each other over cosmic time. Jets also affect the large-scale structure of the universe. They inject energy into galaxy clusters, preventing the hot gas in these clusters from cooling. This influences the distribution of matter on the largest scales. In some sense, black holes aren't just residents of the universe. They're active participants in shaping cosmic structure and evolution. Recently, some researchers have proposed a surprising and controversial idea that supermassive black holes might be connected to dark energy. Dark energy is the mysterious component that makes up about 70% of the universe's total energy density. It causes the expansion of the universe to accelerate, pushing galaxies apart faster and faster over time. We don't know what dark energy is. The simplest explanation is that it's a cosmological constant, a property of empty space itself. But there are other possibilities. Some studies have looked at how the masses of supermassive black holes have changed over cosmic time and found hints that their growth might be linked to the expansion of the universe in unexpected ways. The idea, still very much under investigation, is that black holes might couple to the universe's expansion, gaining mass as the universe expands. If true, this could mean black holes contribute to, or even constitute, a form of dark energy. This is highly speculative. Many physicists are skeptical, and the idea needs much more testing and refinement. But if it holds up, it would be a profound discovery, linking black holes to the ultimate fate of the entire universe. It would mean that black holes aren't just fascinating objects to study. They're fundamental to the cosmos itself, participants in the largest scale dynamics of space-time. Black holes come in different theoretical varieties, depending on their properties. In general relativity, idealized black holes are often grouped into types based on their mass, spin, and electric charge. The simplest is the Schwarzschild black hole, named after Karl Schwarzschild. This is a non-rotating, uncharged black hole. It's perfectly spherical. The event horizon is a sphere at the Schwarzschild radius. This is the solution Schwarzschild found in 1916. If you add rotation, you get a Kerr black hole, discovered by Roy Kerr in 1963. Real astrophysical black holes almost certainly have some rotation, since they form from rotating stars or accrete rotating material. A Kerr black hole is slightly flattened, like the Earth. It has an ergosphere, the region where space-time is dragged around, and it has more complex internal structure than a Schwarzschild hole. If you add electric charge, you get a Reissner-Nordstrom black hole. These are mostly theoretical curiosities. In real astrophysics, any electric charge on a black hole would quickly be neutralized by attracting opposite charges from the surrounding plasma. So astrophysical black holes are expected to be essentially uncharged. The most general solution is the Kerr-Newman black hole, which has both rotation and charge. Again, the charge is probably negligible in realistic situations. For practical purposes, astrophysical black holes are modeled as Kerr black holes with various spins. The spin parameter ranges from 0, a Schwarzschild hole, to the maximum value where the black hole is spinning as fast as physically possible. These different solutions aren't different types of objects in a fundamental sense. They're just different states of the same kind of object, characterized by mass, spin, and charge. One remarkable feature of black holes in general relativity is their simplicity. John Wheeler famously said that black holes have no hair, meaning they can be completely described by just 3 numbers: mass, spin, and charge. Everything else about the matter that formed them, its composition, its structure, its history, is erased. This is called the no-hair theorem. It's been proven under certain assumptions, though physicists continue to explore edge cases and potential violations in extended theories of gravity. The simplicity of black holes is both elegant and puzzling. It seems to imply that enormous amounts of information are lost when matter collapses to form a black hole. This leads directly to one of the greatest puzzles in theoretical physics. Let's talk about one of the deepest mysteries surrounding black holes, the information paradox. In the 1970s, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation means black holes aren't completely black. They glow very faintly with thermal radiation. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass or supermassive black holes, the temperature is incredibly tiny, far colder than the cosmic microwave background. But it's not zero, because the black hole is radiating energy, and energy equals mass through Einstein's E equals mc squared. The black hole slowly loses mass over time. It evaporates. For a stellar mass black hole, this evaporation process would take something like 10 to the 67th years. For a supermassive black hole, much longer. These are times vastly longer than the current age of the universe, about 10 to the 10th years. But in principle, eventually, the black hole would evaporate completely. Here's the problem. Hawking radiation, as originally calculated, is completely thermal. It's random. It carries no information about what fell into the black hole. But quantum mechanics says information cannot be destroyed. If you know the complete quantum state of a system at one time, you should be able, in principle, to calculate its state at any other time. Information is preserved. So what happens to the information about the matter that fell into the black hole? Does it escape somehow in the Hawking radiation? Is it destroyed, violating quantum mechanics? Does it remain hidden inside some remnant after the black hole evaporates? This is the information paradox. For decades, it's been one of the most important unsolved problems in theoretical physics. It sits at the intersection of general relativity, quantum mechanics, and thermodynamics. Many solutions have been proposed. Perhaps information does escape in subtle correlations in the Hawking radiation, in ways the original calculation missed. This is the view many physicists favor today, supported by recent work on the island formula and quantum extremal surfaces in quantum gravity. Perhaps the information is preserved in some quantum structure at or near the horizon, maybe even encoded holographically on the horizon's surface. Perhaps general relativity needs to be modified in extreme conditions, and the interior of a black hole is different from what we think, allowing information to escape. Perhaps evaporating black holes leave behind stable remnants that somehow store all the information. Or perhaps information really is destroyed, and quantum mechanics needs to be modified in the presence of strong gravity. Most physicists are reluctant to give up either general relativity or quantum mechanics. Both theories have been so successful, so the search continues for a resolution that preserves both. Recent progress, particularly from studying black holes in simplified spacetimes and using tools from quantum information theory, suggests that information probably does escape, though we don't yet fully understand the mechanism. The information paradox reminds us that despite all we've learned about black holes, fundamental mysteries remain. Black holes are laboratories where our best theories meet their limits. Understanding them fully will likely require a complete theory of quantum gravity. Related to the information paradox is another puzzle: What is the structure of the event horizon itself? The classical picture from general relativity is that the horizon is a smooth, empty surface. Nothing special happens there locally. An astronaut crossing the horizon of a large black hole wouldn't feel anything unusual at that exact moment. But when you try to combine quantum mechanics with this picture, problems arise. One of the most dramatic proposals is the firewall hypothesis, suggested by physicists including Joseph Polchinski in 2012. The argument goes like this: if information escapes from black holes through Hawking radiation, as quantum mechanics seems to require, then the radiation must be highly entangled with the black hole's interior. But quantum mechanics also has rules about entanglement that limit how much different systems can be entangled with each other. Following these rules carefully leads to a conclusion that seems impossible. There must be an enormous amount of energy, a firewall right at the event horizon, instantly incinerating anything that crosses it. This contradicts general relativity's prediction of a smooth horizon. It's a contradiction between two well-tested theories in a regime where both should apply. The firewall argument is controversial. Many physicists think it reveals a gap in our understanding, rather than a real physical firewall. Perhaps the assumptions going into the argument aren't quite right. Perhaps entanglement works differently than we think in the presence of strong gravity. Or perhaps firewalls are real, and the event horizon is not the smooth, uneventful surface general relativity predicts. Maybe crossing it really is catastrophic, at least for old, evaporating black holes. We don't know yet. The question remains open. There are other ideas about horizon structure too. Maybe the horizon is fuzzy at small scales, with quantum fluctuations in its location. Maybe it's made of quantum bits of information, a quantum membrane rather than a classical surface. Maybe the holographic principle means the horizon is somehow the fundamental reality, and the interior is emergent from quantum information stored on the horizon. These ideas push into territory where we don't have a complete theory. They're informed guesses, windows into the quantum nature of space-time that we're still trying to understand. Not all black holes necessarily formed from collapsing stars or merging matter in galaxies. There's a hypothetical class called primordial black holes that might have formed in the very early universe, shortly after the Big Bang. In the first moments after the Big Bang, the universe was extremely hot and dense, with matter and energy distributed in fluctuations of density. If some regions were dense enough, they could have collapsed directly into black holes, even without forming stars first. Primordial black holes could potentially have a wide range of masses. Some might be tiny, with masses less than Earth's. Some might be stellar mass or larger. They'd be scattered throughout the universe today, remnants of the universe's earliest moments. This is speculative. We have no confirmed detections of primordial black holes, but they remain an intriguing possibility for several reasons. First, they could potentially make up some or all of dark matter, the mysterious substance that makes up about 27% of the universe's mass energy, but doesn't emit or absorb light. If primordial black holes exist in certain mass ranges, they'd be dark, massive objects that could account for dark matter's gravitational effects. This idea has been constrained by various observations. Primordial black holes of certain masses would have observable effects through gravitational lensing, their influence on star formation, or their accretion of gas. So far, these observations have ruled out primordial black holes as the main component of dark matter in many mass ranges. But not all mass ranges are excluded. There are windows where primordial black holes could still exist and contribute to dark matter. Second, if primordial black holes with masses around 30 solar masses exist in significant numbers, they might explain some of the black hole mergers detected by LIGO. Though most physicists think the LIGO black holes formed from stars, the primordial origin hasn't been completely ruled out. Third, very tiny primordial black holes, if they existed, would be evaporating through Hawking radiation today. The smallest ones might have already evaporated completely, potentially releasing energy in ways we might detect. Searches continue. If primordial black holes exist, they'd tell us something important about the early universe, about the distribution of matter and energy shortly after the Big Bang. Let's imagine the far future, an almost incomprehensibly distant future, long after stars have stopped forming, long after galaxies have dispersed, when the universe is cold and dark. In this future, black holes will be the last massive objects, and even they won't last forever. Through Hawking radiation, black holes slowly evaporate. The process is glacially slow for the black holes we know today, but it accelerates as the black hole gets smaller. A stellar mass black hole, say 10 times the sun's mass, would take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros. The current age of the universe is only about 10 to the 10th years, so we're talking about timescales absurdly beyond anything we can intuitively grasp. A supermassive black hole would take even longer, perhaps 10 to the 100th years or more. But eventually, given enough time, they all evaporate. As a black hole loses mass, its temperature increases. The Hawking radiation gets hotter and more intense. The evaporation speeds up. In the final moments, the black hole becomes very small and very hot, radiating energy at an accelerating rate. What happens at the very end? This is one of the great open questions. Does the black hole evaporate completely, disappearing in a final burst of radiation? Does it leave behind some stable remnant, a Planck mass object that can't evaporate further? Does something else entirely happen that we can't predict without a theory of quantum gravity? We don't know. Some physicists think complete evaporation is most likely, that the black hole simply radiates away until nothing is left. Others suggest remnants might exist, stable objects at the Planck scale that somehow encode all the information that fell in. If black holes do evaporate completely, and if information somehow escapes in the Hawking radiation, then in principle, the final state of the universe after a black hole evaporates should be calculable from its initial state. Information would be preserved as quantum mechanics requires. But if information is lost or hidden in remnants, then the evaporation of black holes marks a genuine destruction of information, a violation of quantum mechanics' fundamental principles. This is why the question matters. It's not just about the distant future, it's about the deep laws of physics. The final evaporation of black holes will be, if it happens, among the last significant events in the universe's history. After that, in the far future, the universe will be a cold, dark, ever-expanding void, with nothing but faint radiation and perhaps some quantum fluctuations. It's a melancholy picture, but it's also a reminder of how extraordinary our current epoch is, with stars and galaxies and black holes, with structure and complexity, with the possibility of life and consciousness. Black holes are one of the main reasons physicists are searching for a theory of quantum gravity. General relativity works beautifully for large objects and moderate energies. Quantum mechanics works beautifully for small objects and particles. But when you need both simultaneously, when you have something small and massive like the interior of a black hole, neither theory alone is sufficient. At the Planck scale, roughly 10 to the minus 35 meters and 10 to the minus 43 seconds, quantum effects on space-time itself become important. The smooth fabric of space-time predicted by general relativity should break down, replaced by some quantum structure. Various approaches are being pursued. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings. In string theory, gravity emerges naturally, and black holes can be understood as certain configurations of strings and branes. String theory has had some success in calculating black hole entropy and understanding the microscopic origin of Hawking radiation, at least for certain idealized black holes. Loop quantum gravity takes a different approach, quantizing space-time itself, describing it as a network of discrete loops at the smallest scales. In this picture, the singularity at the center of a black hole might be replaced by a quantum bounce, where matter compressed to Planck, densities bounces back, potentially creating a new region of space-time. Other approaches include causal set theory, which treats space-time as fundamentally discrete and asymptotic safety, which suggests gravity might be consistent as a quantum field theory, after all, under certain conditions. None of these approaches is complete or fully tested. We lack experimental data at the energy scales where quantum gravity becomes important. We can't build particle accelerators powerful enough to probe Planck-scale physics. Black holes provide a natural laboratory where these extreme conditions exist. By studying their properties, their radiation, their horizons, and their effects on space-time, we hope to find clues about the deeper quantum structure of reality. Every mystery about black holes, from the information paradox to the nature of singularities, is ultimately a clue pointing toward the correct theory of quantum gravity. In certain solutions to Einstein's equations, black holes can have even stranger properties than we've discussed so far. Some solutions contain wormholes, tunnels through space-time that connect distant regions or even different universes. A black hole could, in principle, be one mouth of a wormhole, with the other mouth elsewhere. This is the kind of thing that appears in science fiction. Travel through a black hole and emerge somewhere else, perhaps far across the universe. Unfortunately, the realistic prospects are dim. Most wormhole solutions in general relativity are either unstable, collapsing before anything can pass through, or require exotic matter with negative energy density to hold them open. We've never observed anything with negative energy density in nature, though quantum effects can produce it in tiny amounts in special circumstances. Whether enough exotic matter could be gathered to stabilize a traversable wormhole is highly doubtful. Moreover, if you fell into a real astrophysical black hole, you'd encounter the singularity, not a wormhole exit. The wormhole solutions are properties of idealized, eternal black holes in maximally extended spacetimes, not the collapsing stars and accreting systems we observe. Still, wormholes remain fascinating theoretical objects. They teach us about the structure of spacetime, about causality and about the limits of what physics allows. There are also more speculative ideas about white holes, the time-reversed version of black holes. While black holes trap everything that crosses the event horizon, a white hole would be a region from which matter and light can escape, but nothing can enter. White holes probably don't exist in nature. They're unstable and would quickly convert into black holes. But they're mathematically valid solutions to Einstein's equations, and they help us understand the time reversal properties of general relativity. Black holes are the ultimate testing ground for general relativity. In the vicinity of a black hole, gravity is at its strongest. Space-time curvature is at its most extreme. If general relativity is going to break down or show deviations, this is where we'd expect to see it. So far, every observation agrees with the theory. The orbits of stars around Sagittarius A star follow the paths predicted by general relativity precisely. The sizes and shapes of black hole shadows match the predictions. Gravitational waves from merging black holes carry exactly the signatures Einstein's equations predict, down to incredible precision. The ring down of merged black holes, where the final black hole settles down by emitting gravitational waves, provides a particularly clean test. The frequencies and damping times depend only on the final black hole's mass and spin. They're like the ringing of a bell, and the tone tells us everything about the bell. So far, every merger detected has rung exactly as general relativity says it should. Scientists continue to look for deviations. They test whether the speed of gravitational waves equals the speed of light, as the theory requires. They check whether black holes really have no hair, whether 3 parameters are truly sufficient to describe them. They look for signs of exotic matter or modified gravity theories. All tests so far support general relativity. The theory is now over a century old, and it continues to pass every challenge we throw at it. But this doesn't mean we should stop testing. Science progresses by pushing theories to their limits, by finding the boundaries where they break down. And we know general relativity must break down somewhere, because it's incompatible with quantum mechanics at the smallest scales. Black holes are where we're most likely to find that boundary. Let's talk about the broader role black holes play in the cosmos, particularly in shaping galaxies. We now know that supermassive black holes and their host galaxies co-evolve. There's a strong correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, particularly the velocity dispersion of stars in the galactic bulge. This correlation wasn't predicted. It was discovered through observations, and it suggests a deep connection between the growth of the black hole and the growth of the galaxy. How does this work? As a supermassive black hole accretes matter, it releases enormous amounts of energy. Some of this energy goes into heating the surrounding gas and driving powerful winds and jets. These winds and jets can blow gas out of the central regions of the galaxy, or heat it so much that it can't cool down and collapse to form new stars. This provides negative feedback. The black hole's activity suppresses further star formation and limits both the galaxy's growth and the black hole's own food supply. Without this feedback, simulations of galaxy formation don't work properly. Galaxies form too many stars too quickly, creating galaxies that look nothing like the ones we observe. The supermassive black hole acts as a regulator, a thermostat keeping the galaxy in balance. When the galaxy tries to form stars too rapidly, the black hole turns on, heats things up, and slows everything down. This is why nearly every large galaxy has a supermassive black hole at its center. Not because black holes somehow prefer galactic centers, but because the black hole and the galaxy grew together, each influencing the other's development. When galaxies collide and merge, as happens frequently in the universe, their central black holes eventually sink to the center of the merged galaxy and form a binary system. Over time, through interactions with stars and gas, and ultimately through the emission of gravitational waves, these binary black holes spiral together and merge. The merger produces gravitational waves that we can detect with instruments like LIGO, and, in the future, space-based detectors like LISA. It also produces a single, more massive black hole, often with a substantial kick from the asymmetric emission of gravitational waves. In rare cases, this kick might be strong enough to eject the black hole from the galaxy entirely, creating a wandering supermassive black hole traveling through intergalactic space. The study of how black holes and galaxies co-evolve is one of the most active areas of modern astrophysics. It connects the smallest scales, the event horizons of black holes, to the largest scales, the structure and evolution of the entire universe. Let's return to one of the most important ways we detect stellar mass black holes: X-ray binaries. In these systems, a black hole orbits a normal star. The two are locked in a gravitational dance, circling their common center of mass. As the black hole's gravity pulls gas from the companion star, that gas doesn't fall straight in. Because both objects are orbiting, the gas has angular momentum. It spirals inward, forming a flat, rotating disk called an accretion disk. The physics of accretion disks is complex. Gas spiraling inward experiences friction, with adjacent layers moving at different speeds. This friction heats the gas tremendously. In the inner regions of the disk, close to the black hole, the gas reaches temperatures of millions of degrees Kelvin. At these extreme temperatures, the gas emits primarily in X-rays, high-energy photons far more energetic than visible light. This is what makes X-ray binaries so bright in X-rays, despite being relatively faint in visible light. The X-ray emission isn't steady. It flickers and varies on timescales from milliseconds to days, depending on the processes in the accretion disk. Some of this flickering is quasi-periodic, showing nearly regular oscillations that carry information about conditions very close to the black hole. By studying these X-ray variations, astronomers can probe the environment just outside the event horizon. They can measure how fast the disk is rotating, test whether the inner edge of the disk really is at the innermost stable circular orbit predicted by general relativity, and even estimate the black hole's spin. The companion star in these systems gradually loses mass as the black hole pulls gas away. Eventually, over millions or billions of years, the star might be completely consumed, leaving only the black hole behind. But new X-ray binaries continue to form as black holes encounter or capture new stellar companions. These systems are laboratories for studying black hole accretion, relativistic jets, and the physics of matter in extreme gravitational fields. Cygnus X1 remains one of the most studied X-ray binaries. Decades of observations have pinned down the black hole's mass at about 21 solar masses, and its spin at close to the maximum allowed by general relativity. The companion star is a massive blue supergiant, slowly feeding its outer layers to the black hole. Our own galaxy, the Milky Way, hosts a supermassive black hole at its center. We call it Sagittarius A star, or SGR A star for short. For most of human history, we didn't know it was there. The galactic center is about 26,000 light-years away, and it's hidden behind dense clouds of dust that block visible light. But in the latter half of the 20th century, astronomers developed ways to peer through the dust using radio waves, infrared light, and X-rays. What they found was a compact, intense radio source at the exact center of the galaxy. In the 1990s, Andrea Ghez and Reinhard Genzel began separate programs to track individual stars in the galactic center, using large telescopes with adaptive optics to correct for atmospheric blurring. Over years and decades, they watched stars orbit the center of the galaxy. One star in particular, S2, has an orbital period of just 16 years. At closest approach, it comes within about 17 light hours of the galactic center, traveling at more than 7,000 kilometers per second, about 2.5% of the speed of light. By carefully measuring S2's orbit, along with the orbits of dozens of other stars, the teams could use Newton's and Einstein's laws to calculate the mass of whatever they're orbiting. The answer, about 4 million solar masses, all concentrated in a region smaller than the orbit of Mercury around the Sun. There's nothing visible there in optical wavelengths. No dense cluster of stars that could account for the mass. No luminous gas cloud. Just empty space, gravitationally speaking, with this enormous, invisible mass at the center. The only explanation consistent with all observations is a supermassive black hole. Sagittarius A star is usually quite dim, especially compared to active galactic nuclei in other galaxies. It's not actively feeding on large amounts of gas. Most of the time it's quiet, with only a trickle of material falling in. Occasionally, though, it flares. The X-ray and infrared emission suddenly brighten by factors of tens or hundreds, then fade over hours. These flares are thought to be caused by magnetic reconnection events, or the acceleration of small amounts of gas in the turbulent environment near the event horizon. In 2022, the Event Horizon Telescope released an image of Sagittarius A star's shadow, complementing the earlier image of M87 star. Because Sagittarius A star is much smaller and the material around it changes rapidly, creating this image was even more challenging. The team had to develop new techniques to handle the variability, but the result was worth it. The image shows a ring of emission with a dark center, just as expected. The size of the ring, about 52 microarc seconds in angular diameter, matches the predictions of general relativity for a 4 million solar mass black hole at that distance. We live in a galaxy with a supermassive black hole at its heart. It's not a threat. We're far too distant to be affected. But it's a reminder that these exotic objects aren't just distant curiosities in other galaxies. There's one right here in our cosmic neighborhood. Between stellar mass black holes and supermassive ones, there's a mysterious middle ground, intermediate mass black holes. These would have masses from about 100 to 100,000 times the Sun's mass. They should exist. The question is, where and how many? Finding intermediate mass black holes is difficult. They're too massive to form directly from a single star's collapse. but too small to be the giants at the centers of large galaxies. One place to look is in dense star clusters, particularly globular clusters, which are ancient, tightly packed collections of hundreds of thousands of stars. In these dense environments, stars can collide and merge. Over time, repeated collisions might build up increasingly massive objects. Eventually, this process could create an intermediate mass black hole at the cluster's center. There have been some tentative detections through various methods. Unusual stellar velocities near the centers of certain globular clusters hint at the presence of unseen massive objects. Some ultra-luminous X-ray sources in other galaxies, which are too bright to be explained by stellar mass black holes, might be intermediate mass ones. Gravitational wave detectors have also found a few merger events involving black holes in this mass range, confirming that such objects exist, even if we don't fully understand how they formed. Intermediate mass black holes might also be the seeds that grew into supermassive black holes in the early universe. Understanding how they form and evolve could help explain how supermassive black holes grew so large so quickly. But detailed observations remain challenging. Intermediate mass black holes in our galaxy would be rare and hard to distinguish from other phenomena. Those in other galaxies are difficult to confirm without very high-resolution observations. As our instruments improve, we expect to find and characterize more of these middleweight black holes, filling in the gap between stellar and supermassive varieties. Sometimes, a star wanders too close to a supermassive black hole. When this happens, the outcome is dramatic: a tidal disruption event. As the star approaches, tidal forces become stronger and stronger. Remember, tidal forces arise because gravity is stronger on the side of the star closest to the black hole than on the far side. There's a critical distance called the tidal radius, where the tidal forces become strong enough to overcome the star's own gravity holding it together. If the star crosses this radius, it's torn apart. The disruption isn't gentle. The star is stretched into a long, thin stream of gas. Part of this stream is flung out into space at high velocity, escaping the system entirely, but roughly half of the stellar material remains bound to the black hole. This bound material curves back around and falls toward the black hole, forming an accretion disk. The disk heats up and becomes luminous, emitting intense radiation across the electromagnetic spectrum. From a distance, we see a sudden brightening in the galactic nucleus. What was a quiet or dormant black hole suddenly flares into brilliance, sometimes outshining the entire galaxy for weeks or months before gradually fading. Astronomers have detected dozens of tidal disruption events in recent years, thanks to surveys that repeatedly image large portions of the sky looking for transient phenomena. Each event provides information about the black hole's mass and spin, the properties of the disrupted star, and the physics of how material accretes onto black holes. Tidal disruption events also provide a way to find and study supermassive black holes that would otherwise be difficult to detect. Even if a black hole isn't normally active, a chance stellar encounter can temporarily light it up. The unfortunate star is completely destroyed. Its atoms, once fused in the star's core or forming its atmosphere, are scattered, some into space, some into the accretion disk, where they'll eventually cross the event horizon and be lost forever. It's a violent process, but it's also a natural consequence of having supermassive black holes at the centers of galaxies. With hundreds of billions of stars in a typical galaxy, and orbital dynamics gradually scattering some into the central regions, these events happen regularly across the universe. Black holes can rotate, and their spin is one of their most important properties. When a massive star collapses, it usually has some angular momentum, some rotation. That rotation doesn't disappear. It's conserved, compressed into the black hole, causing the black hole to spin. Similarly, when black holes merge, the final black hole typically spins, with its angular momentum depending on the spins and orbital motion of the merging pair. A black hole's spin is characterized by a dimensionless parameter that ranges from 0 for a non-spinning Schwarzschild black hole to 1 for a maximally spinning Kerr black hole. The spin has profound effects on the space-time around the black hole. A spinning black hole drags space-time around with it through frame dragging. This affects the orbits of particles, the behavior of accretion disks, and the emission of jets. The innermost stable circular orbit, the closest a particle can orbit without falling in, depends on the spin. For a non-spinning black hole, it's at 3 times the Schwarzschild radius. For a maximally spinning one, it can be much closer, right down to the event horizon itself for orbits in the same direction as the spin. This means more gravitational energy can be extracted from material falling into a spinning black hole. The accretion efficiency is higher, which makes spinning black holes potentially brighter when they're actively feeding. Measuring black hole spin is challenging but possible. Several methods exist. One approach uses the X-ray spectrum from the accretion disk. Iron atoms in the disk emit X-rays at a characteristic energy, but these X-rays are Doppler shifted and gravitationally affected in complex ways that depend on the disk's inner edge, and thus on the black hole's spin. By carefully modeling the distorted iron line, astronomers can estimate the spin. This has been done for several stellar mass and supermassive black holes, with results ranging from slowly spinning to near maximal spin. Gravitational wave detections also provide spin information. The waveform from a merger depends on the spins of the 2 black holes before the merger and determines the spin of the final black hole. LIGO and Virgo observations have shown that stellar mass black holes in merging binaries have a range of spins. Some are spinning rapidly, others slowly. This diversity tells us something about how these systems formed and evolved. The spin of supermassive black holes probably reflects their accretion history. A black hole that grew primarily by accreting gas in a coherent, orderly way from a disk might spin rapidly. One that grew by chaotic mergers from various directions might have a lower net spin. Understanding black hole spin helps us understand their formation, their effects on their surroundings, and the fundamental physics of rotating spacetimes. When 2 black holes orbit each other, they form a binary system. Over time, these binaries lose energy and spiral together, eventually merging in a spectacular event. For stellar mass black holes, binaries can form in several ways. 2 massive stars in a binary system might both explode as supernovae, leaving behind 2 black holes in orbit, or black holes might capture each other in dense stellar environments like globular clusters. Once formed, the binary gradually loses energy. If the black holes are isolated in space, this happens through the emission of gravitational waves. The black holes spiral inward slowly at first, taking potentially billions of years to get close. But as they approach each other, the process accelerates. The gravitational wave emission grows stronger, carrying away energy and angular momentum faster and faster. The black holes spiral inward more rapidly. In the final moments, they're orbiting each other at a significant fraction of the speed of light, circling hundreds of times per second, closer and closer until their event horizons merge. The merger itself takes a fraction of a second. The two horizons touch and merge into one. Gravitational waves sweep outward, carrying information about the masses, spins, and final merger. The resulting black hole is initially highly distorted, not a smooth sphere. It vibrates and radiates gravitational waves as it settles down into a final, stable, rotating black hole. This ring-down phase provides a clean test of general relativity's predictions. The final black hole's mass is slightly less than the sum of the two original masses. The missing mass, typically a few percent of the total, was radiated away as gravitational wave energy during the merger. This is E equals mc squared in action on a cosmic scale. A few solar masses of pure energy, released in a fraction of a second, creating the most powerful explosions in the universe, except for the Big Bang itself. For supermassive black holes, the merger process is similar, but happens on much longer timescales. When two galaxies collide, their central black holes are initially separated by thousands of light years. Over hundreds of millions of years, dynamical friction with stars and gas causes the black holes to sink toward the center of the merged galaxy. Eventually, they form a binary, orbiting each other at distances of light years or less. The final approach from light year separation to merger is more complicated for supermassive black holes. Gravitational wave emission alone isn't efficient enough at large separations. The binary needs interactions with stars and gas to lose energy and shrink further. This is called the final parsec problem, and it's still being studied. How exactly do supermassive black holes get from separations of light years to separations close enough that gravitational waves can finish the job? Various mechanisms have been proposed. Scattering of stars past the binary, interactions with gas disks, three-body interactions with a third black hole. In practice, different mechanisms probably operate in different systems. Eventually, the black holes do merge. The gravitational waves from supermassive black hole mergers have wavelengths of months to years, too long for ground-based detectors like LIGO. Future space-based detectors like LISA are designed specifically to detect these low-frequency gravitational waves. When LISA launches, probably in the 2030s, it should detect supermassive black hole mergers across cosmic time, providing a census of how these giants grew and merged throughout the universe's history. Let's zoom out and think about black holes in the context of the entire observable universe. The observable universe has a radius of about 46 billion light years. That's not a mistake. Even though the universe is only about 13.8 billion years old, the expansion of space means we can see objects much farther than 13.8 billion light years away. Within this observable universe, there are hundreds of billions of galaxies. Most large galaxies host supermassive black holes. Many galaxies also contain millions of stellar mass black holes. The total number of black holes in the observable universe is staggering. Estimates suggest 10 to the 18th power stellar mass black holes, a billion, plus hundreds of billions of supermassive ones. These black holes are spread throughout space at all distances. When we look at distant galaxies, we're seeing them as they were long ago, because light takes time to reach us. Some of the black holes we're observing existed when the universe was young, less than 1 billion years old. Black holes are an integral part of cosmic structure. They influence star formation, shape galactic centers, and release enormous amounts of energy that affects the intergalactic medium. But there's more to the universe than we can see. Beyond the observable universe, space continues, possibly forever. If the universe is infinite, as some cosmological models suggest, then there are infinite black holes, infinite galaxies, infinite stars. We can't see beyond the observable universe. Light from those regions hasn't had time to reach us yet, and it never will, because the expansion of space is carrying those regions away faster than light can travel toward us. So when we talk about the total number of black holes, we usually mean within the observable universe. It's the only part we can study. It's humbling to think that all the black holes we know about, all the ones we've detected and studied, are just the tiniest fraction of what exists. The vast majority of black holes are too distant, too faint, or too quiet for us to ever detect. They're out there, though, dark, compact masses scattered throughout the cosmos, remnants of dead stars and ancient galaxies, warping space-time and quietly existing in the depths of space. What is the ultimate fate of black holes, and what do they tell us about the universe's end? In the far future, many trillions of years from now, the universe will be very different from today. Star formation will have ended, galaxies will have dispersed or merged, the universe will be cold, dark, and empty. But black holes will remain. They'll be the last massive objects, slowly evaporating through Hawking radiation. A stellar mass black hole takes about 10 to the 67th years to evaporate. Supermassive ones take even longer, 10 to the 100th years or more. These are timescales almost beyond comprehension. The current age of the universe, 13.8 billion years, is nothing compared to them. By the time black holes evaporate, the universe will be billions of times older than it is now, possibly trillions of times older. During this time, the expansion of the universe continues. Space stretches, galaxies, and even the remnants of galaxies move apart, eventually separating beyond each other's cosmic horizons. In the end, each region of space will contain perhaps just a single black hole, alone, evaporating slowly into an ever emptier universe. When the last black holes finally evaporate, what's left? Just a dilute gas of photons and other particles, growing ever more dilute as expansion continues. Eventually, the temperature of the universe approaches absolute zero. This is sometimes called the heat death of the universe. All usable energy has been radiated away. No structures remain, no stars, no planets, no black holes. Just an infinitely large, infinitely cold, infinitely dark expanse. It's a bleak picture, though we should remember it's speculative. We don't know for certain what will happen in such distant futures. Our understanding of physics might be incomplete. Perhaps dark energy will change over time, altering the universe's expansion. Perhaps quantum effects we don't understand will become important. Perhaps new structures or phenomena will emerge that we can't predict. But based on what we know now, black holes represent a transition point in cosmic history. They're the last remnants of an era of structure and complexity. Their evaporation marks the end of that era and the beginning of an eternal, empty darkness. Yet even this ending has a kind of majesty. The fact that we exist now in an epoch when stars shine and black holes form, when structure and complexity and life are possible, is extraordinary. The universe won't always be like this. But right now, it is, and we're here to witness it. We've traveled far in this exploration, from the earliest ideas about dark stars to modern observations of black hole shadows, from the mathematics of Einstein's equations to the quantum mysteries of the information paradox. Black holes stand at the edge of our understanding. They're regions where our best theories meet their limits, where the known laws of physics break down. They're also some of the most fascinating objects in the universe, not despite their mysteries, but because of them. A black hole is simple in its description: mass, spin, and charge. 3 numbers. Yet these 3 numbers encompass phenomena of stunning complexity and beauty. Space-time twisted into impossible shapes, light bent into rings and arcs, time flowing at different rates, matter compressed to infinite density, information perhaps encoded on surfaces, energy extracted from rotation, jets launched across millions of light years. Black holes are violent and destructive, but they're also creative. They regulate star formation. They shape galaxies. They drive some of the most energetic phenomena in the cosmos. They may even be connected to the expansion of the universe itself. We've learned so much about them in the past century. We've gone from speculation to confirmation. We've detected them, measured them, imaged them, heard them merge through gravitational waves. Yet fundamental questions remain. What happens at the singularity? How is information preserved or lost? Do firewalls exist? What is the quantum structure of space-time? How did supermassive black holes form so early? What happens in the final moments of evaporation? These questions drive modern physics. They inspire new theories, new experiments, new observations. They push us to the boundaries of knowledge. That's what makes black holes so compelling. They're not just objects to study. They're windows into the nature of reality itself. Every black hole is a natural laboratory where conditions exist that we could never create on Earth, where gravity is strong enough to compete with quantum mechanics, where space-time itself becomes dynamic and dramatic. By studying black holes, we're studying the universe at its most extreme. We're testing our theories in conditions as far from everyday experience as possible. We're asking the deepest questions about space, time, matter, and energy. In a very real sense, black holes are teachers. They reveal the universe's secrets to those patient and clever enough to listen. The journey isn't over. We'll continue to observe, to measure, to theorize. We'll build better detectors, more powerful telescopes, more sophisticated simulations. We'll probe deeper into the mysteries. Perhaps one day, we'll understand black holes completely. We'll have a quantum theory of gravity that explains the singularity, resolves the information paradox, and predicts phenomena we haven't yet imagined. Or perhaps black holes will always retain some mystery. Perhaps there are limits to what we can know, boundaries we can never cross, questions we can never fully answer. Either way, the pursuit matters. The questions matter. The attempt to understand matters. Because in studying black holes, we're really studying ourselves. We're exercising our capacity for wonder, for curiosity, for systematic investigation of the unknown. We're participating in a grand tradition that stretches back to the earliest humans who looked at the night sky and asked, "What's out there?" A tradition that includes John Mitchell calculating dark stars by candlelight, Carl Schwarzschild solving equations in a wartime trench, and thousands of scientists today coordinating telescopes across the planet to image the unseeable. Black holes remind us that the universe is far stranger and more wonderful than everyday experience suggests. That reality has depths and complexities we're only beginning to fathom. They remind us that we live in a cosmos where matter can compress to infinite density, where time can stop, where information might be encoded on surfaces, where two massive objects can collide and shake the fabric of space itself. They remind us that we don't know everything. That mystery remains, that the frontier of knowledge is still out there, waiting. And perhaps most importantly, black holes remind us that we're part of this universe, made of matter that came from stars, looking out at the cosmos with minds that arose from natural processes, asking questions about our place in it all. The universe created structures complex enough to wonder about themselves. Atoms arranged into molecules, molecules into cells, cells into brains that can contemplate black holes and space-time and infinity. That's remarkable. That's beautiful. That's a story worth telling. So as you drift off to sleep tonight, think about the universe. Think about black holes, those strange regions where the rules change and reality bends. Think about the fact that we exist in a cosmos vast and ancient, full of wonders we're still discovering. And rest easy, knowing that somewhere out there in the darkness, black holes are spinning, merging, growing, evaporating, shaping galaxies, warping space-time, existing at the edge of reality, waiting for us to understand them. Thank you for joining me on this journey. Sweet dreams.